So level 13.2, we are going to talk about permutations and combinations. So the distinction that we are going to be working with is if order matters or if order doesn't matter. If things are distinct or if they are non-distinct, if you can tell two things apart. So, and also if there's repetition is allowed or there's no repetition allowed. So with all that being said, permutations, order of arrangements. It's an order, so order matters. Order matters with permutations. So we have three different types of permutations that we're going to talk about. We have distinct objects with repetition. We have distinct objects with no repetition. And we have not distinct objects, which means we can't tell them apart. So the first example that we're going to do, and it's going to build off of what we did before. International Airline Transportation Association has three-letter codes to represent airport locations. So like Detroit's DDW, Fort Lauderdale is FLL. Repetition is allowed. So how many airport codes are possible? Well, we have three codes, and they all use letters. So we could have 26, 26, 26, which is 26 to the third power. And if we go to our calculator, which I'm going to do off screen, 26 to the third is 17,576. So if you think you have something that has a distinct, each letter is distinct, right? We could have F, 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 or we could have D, A, S. All of those are distinct letters. With repetition means you could do A, A, A. It would be however many different elements you have. So the number of things you have to how many spaces you have, n to the r. Okay, so that's the first one we're going to talk about. Suppose that we wish to have three-letter codes using the 26 uppercase letters of the alphabet, but you don't want any one to be used more than once. So no repetition. So this is no repetition. How many different three-letter codes could you have? Well, in this case, you have 3 spots. You have 26 choices for the first one. You could have A through Z. So you pick A, well now you only have 25 choices. After that you have 24 choices, and then you're done. So the number of ways that you could arrange this is 26 times 25 times 24, which is 15,600 ways, which is a lot less. Note, this is what we call a permutation. So this is an ordered arrangement, and we can't have a repetition. So you'll often see this notation written, permutation, N permute R things. We have N different letters, R ways. So we have 26, 25, 24 over 3 spots. If we went to our calculator just as a proof of concept, and I zoom in here for you, if you hit menu, and then you go down to 5, and then you go down to permutation, it has that NPR, and what we could do is 26, and then you hit this comma button, which is right under pi. So 26 letters permuted 3 different ways, we get the same number. So just want to clarify that to make our lives easier moving forward. So we always want R to be less than or equal to N, and repetition is not allowed. So here we go. How many ways can 5 people be lined up? So one of the ways to think about this, we have 5 spots. That is 5. 5 people could be in the first spot, then 4, because the same person can't stand in the same spot. 3, 2, 1. Another fancy way when this happens is writing 5 factorial. This exclamation point is not an excited 5. It is factorial. Hopefully you've seen that before. If I go to my calculator, I believe it's under this symbol right next to the G. If I type 5 and then I go to the exclamation point and hit enter, what's happening there is 5 times 4 times 3 times 2 times 1. As I've said many times before, mathematicians are inherently lazy. So the shortest way they can find to write something, they will. So whenever you see this exclamation point after that number, which that's equal to 120, that's 5 times 4 times 3 times 2 times 1. All right, flip it over. So what's happening here with permutations of our objects, or our object chosen from n distinct objects without repetition, blah, 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 blah. So n objects are distinct. That means like our letters. An object is chosen only once and can't be repeated. And order is important here. These are the three factors for permutations. If that's the case, this is what the formula is doing. We're taking n factorial divided by n minus r factorial. So when we do permute n comma r, it's doing n factorial over n minus r factorial. So I'm going to write these out, but you could easily just use your calculator. So what's happening here when you have a permutation? You have 7 factorial over 7 minus 3 factorial. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 minus 3 is 4 factorial, so that's 4 times 3 times 2 times 1. What's nice is these 4's cancel, these 3's cancel, these 2's cancel, these 1's cancel, and you're just left with 7 times 6 times 5, which in our case is 210. 6 permute 1. I'm going to write out the formula, 6 factorial over 1 factorial. Well, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 over 1. These ones cancel. And you have 720. Now, I made the most common mistake here is it's not just 6 factorial over 1 factorial. This is 6 minus 1 factorial, which is 5 factorial. So this is 5 times 4 times 3 times 2 times 1, which a lot more things cancel out. So this is just 6. Now if we think about this, we have 6 objects in one spot. It's just 6 number of ways people could go in that spot. How about 52 cards? We're going to pick 5 of them. So we could look at it 3, 4, 5. Could have 52, 51, 50, 49, 48. So that's our permutation. That's how we did it before. If we wrote out the formula, that would be 52 factorial over 52 minus 5 factorial, which is 52 factorial over 47 factorial. Either way, if we typed in this, or if we went to menu 5 permutations and we did 52 comma 5 and hit enter, we're going to get the exact same answer. Okay, so I just wanted to show you a bunch of different ways. What we were doing before is exactly what we're doing now. Just a couple different ways of calculating that. So the third different case that we were talking about, where objects are not distinct, we have a slightly different condition. Okay, so if you have a permutation, so we're arranging things, but the objects aren't distinct, which means, let's say we're rearranging the letters in a word. Well, we may have repeats. In order to take account for those repeats, we need to divide out by each kind of different way we could have those letters. So we're going to do this as an example, and then I'm going to bring up this formula. How many different ways can you rearrange the letters in the word rearrange? Now, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 letters in there. We have 1, 2, 3 R's. So those are non-distinct. We have 1, 2 E's. We have 1, 2 A's. And we have, well, I can write it. It's kind of, doesn't mean anything. We have 1N. So if we take account any repeats and we divide those out, the number of different ways you could rearrange the letters in rearrange. And I'm just going to go to my calculator and I'm going to show you. We have 9 factorial divided by 3 factorial times 2 factorial times 2 factorial. If I hit enter, I have 15,120 ways, which is a lot. 15,120 ways of rearranging the letters in rearrange. So how about Mississippi? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 letters in Mississippi. The M only happens once. The I happens 1, 2, 3, 4. 4 I's. I have 1, 2, 3, 4. 4 S's. I have 1, 2 P's. So, again, if we go to our calculator and we hit division, we have 11 factorial over 4 factorial times 4 factorial times 2 factorial. There are 34,650 ways. 34,650 different ways of rearranging the letters in Mississippi, which is crazy. All right, moving on to combinations. I know the problems are here, but I want to make sure that we do these together. So with combinations, and I know I have this as a part 2, but this is only a 1-pager, so this should go really quick. Combinations. Order does not matter. So I'm just going to write this big and bold. Order does not matter. So we were spending all of our time worrying about order with permutations. Combinations, order doesn't matter. We have the same or similar notation. We have n distinct objects. An object is used, it cannot be repeated, and order is not important. So this is our formula. We have n factorial over n minus r factorial divided by r factorial. So there's a second thing. So list out all of the combinations of the 4 objects A, B, C, D taken 2 at a time. And then we're going to do what is 4 choose 2. So does order matter here? If we have A and B, it's the same thing as B and A. So we have A, B, we have A, C, we have A, D, then we have B, C, we have B, D, and we have C, D. AB, AC, AD. We have 6 different ways. Now, if we use this formula up here, we have 4 factorial over 4 minus 2 factorial, 2 factorial, which is 4 factorial over 2 factorial, 2 factorial. Now I'm just going to write this out. 2, 1 over 2 times 1, 2 times 1. Those cancel. This becomes 2, that becomes 1. So 2 times 3 is 6. Now 6, we have 1, 2, 3, 4, 5, 6. 6 different combinations. This reduced our number way down. If I go to my calculator and I hit menu, 5, and go down to combination, and I do 4, comma, 2, I get 6. So combinations, when order doesn't matter, significantly drops the number of ways we can do things because it relinquishes us from saying AB is different than BA. So I'm going to write out the setup and then we're going to do these as much as we can on the calculator. So if order does not matter, 3 choose 1. So you read this as 3 choose 1. we have 3 factorial over 3 minus 1 factorial, 1 factorial, which is 3 factorial, 2 factorial, 1 factorial, which should just be 3. So I'm going to go to my calculator, and I'm just going to change it to 3, 1, and I get 3. If I do 6 choose 3, I have 6 factorial over 6 minus 3 factorial, 3 factorial, which is 6 factorial, 3 factorial, 3 factorial. 6 choose 3 is 20. If I have n factorial, so I have n factorial over n minus 0 factorial, 0 factorial. Now you might be saying, well, anything times 0 is 0. 0 factorial, by definition, is 1. So if I have n factorial over n factorial, 0 factorial, these cancel, and I'm just left with 1. Because if I have n of anything, and I'm picking none of them, I should only have one way of doing that. That is the null set, which makes sense. Last one. 52 choose 5. 52 choose 5 is 52 factorial over 52 minus 5 factorial, 5 factorial. We repeat it again. Now I've already typed that into my calculator. As you can see, 2,598,960. Now, if 52 choose 5 looks familiar, this is the number of ways you can have a 5-card hand. Order doesn't matter in how they appear, because if you have a king, jack, 3, king, 5, you still have 2 kings. It doesn't matter that they came together or separately. Last one on this page. In how many ways can a committee be formed from a pool of 7 students? Well, it should be a committee of 3 be formed by 7 students. Now, if you have just someone that's working on a committee and you need 3 people on there, it doesn't matter who goes first, who goes second, who goes third. If order doesn't matter, this is going to be a combination instead of a permutation, which means we have 7 choose 3, and 7 choose 3, if I just go up here, I can write out the formula, but I'm just going to go straight to my calculator. 7 choose 3 is 35 ways you can pick that. All right, good luck on the problems.